All right. Good afternoon, everyone. Thanks for joining us today. Our seminar speaker is Dr. Kevin Arrigo. He's a professor at Stanford University in the Department of Earth System Sciences. Kevin got his undergraduate degree in natural resources at the University of Michigan, and he did his PhD at University of Southern California in biological sciences. He went on to do a postdoc at the NASA Goddard Space Flight Center and then stayed on there for a few years as a civil servant before getting his first position as an assistant professor at Stanford, where he's been ever since. So Kevin is a biological oceanographer, and he studies the microbial processes in polar ecosystems. And today he's going to be sharing some of his recent work with us today. So thank you so much for joining us, Kevin.
I just want to say before I start that if anybody has any questions about anything that I put up, don't be shy about asking. I'm happy to answer anything you might need to know. So today's talk is really about something that probably most of you have never heard of before. When we talk about phytoplankton blooms in the Arctic, everybody's heard, of course, that the Arctic is changing rapidly, the ice is melting, all these things are happening. And it turns out that's, not surprisingly, affecting the phytoplankton as well. And so what we're interested in is how is it affecting the timing of the phytoplankton, and not even so much the typical phytoplankton we might be normally thinking of, the stuff that lives in the open ocean. We're going to focus a lot on phytoplankton that are actually living under the ice. And these are not ice algae, but these are phytoplankton blooms. And so I'll be talking a lot about that today. And so I'm going to start with what is an under ice phytoplankton bloom. How many people have heard of under ice phytoplankton blooms? Oh, good for you. All right. So they haven't been talked about, well, actually a little bit they've been talked about for a while, but it's only been recently that they've been on people's radar screen. So we'll talk about what it is, how do we define a phytoplankton bloom under the ice. We'll look at some historical context of them, present 2 case studies. Actually, I was part of both of them, but I was really directly involved in the second one. We're going to look at what's driving under ice phytoplankton blooms. How can we detect them? This is a big problem. A lot of what I do is satellite remote sensing. And so I've published many papers on productivity of the Arctic from satellites. Of course, you can't see phytoplankton blooms under the ice from a satellite. So that's a big problem. So we need to find other ways to detect these things if we want to detect them. We're going to look at how widespread might they be. And finally, why do they matter? So this is a typical phenology, which means just the seasonal cycle, the timing of phytoplankton in the Arctic. This is from Paul Waspin, 1991, and it's pretty much conventional wisdom ever since. I mean, you can still see papers published today that use this exact same diagram. And the way it goes is that it's dark in the winter, not much is going on in terms of phytoplankton. Finally, the sun comes up. As the sun comes up, it gets a little bit brighter, but there's still lots of snow and sea ice around, so no phytoplankton activity going on under the ice. At some point, the light gets enough that algae can start to grow in the ice, and that's actually what I got my PhD on, was studying the algae in the ice. Eventually, those algae melt away, they fall to the bottom, and it's taken over by this phytoplankton bloom that takes over in the open water. And then eventually, the sun goes down, the ice grows back, and the phytoplankton bloom ends. And that's typically the way people think about productivity in the Arctic, where production is largely restricted to the open water, and there's very little productivity under the ice. And so what is a under ice phytoplankton bloom? This may seem like an obvious definition, but it's not as obvious as you might think. It's one that develops under the ice. So when we made the first discovery of the really large under ice phytoplankton bloom in 2011, people were very critical of our study because they said, no, that's probably not, it probably didn't develop under the ice, it probably just advected from open water under the ice, and that's what you're seeing. Other people said, no, it's probably not a phytoplankton bloom under the ice, it's just ice algae that have fallen off the ice into the water. Well, what we're going to call an under ice bloom is one that develops in the water column under the ice. It didn't advect there, it didn't fall from the ice there, it grew there. Anything else is not an under ice phytoplankton bloom. Now, there's been a little bit of history looking at things that are kind of under ice phytoplankton blooms. Here's one here. This is by Louis Legendre in 1981. And this is in Hudson Bay, and what this is a vertical, this is just a vertical depth profile of salinity showing really low salinity meltwater layers right at the surface. This is about 5 meters. It's a very thin layer. And this is all under 100% ice cover. And what they showed is just what the chlorophyll concentration did during these stations in February, March, April, and then in May. And this is under the ice. It was pretty high chlorophyll concentrations under the ice, but it was only in this really, really thin layer under the ice. So this is kind of an under ice bloom, but it's not what you're going to see as typical for what we see now. There was another study, 1996. This was in the Chukchi Sea, and this was even thinner. So this is depth here. This is ice. This is a lead, basically an open water area in between two ice flows. And you can see here's this under ice brackish water pond, and there was a really intense algal bloom going on in this water. But it's only a meter thick, right? It's a really thin bloom. It wasn't until 1996 where we saw something that really looked like a substantial bloom. So this was in the Barents Sea, and this is distance along a cruise track. This is depth down to 350 meters, and this is chlorophyll concentration. And so the dark areas are areas of high phytoplankton concentration. This is where the sea ice was. So you could see, this is about 100 or so kilometers. So it's under the ice. It's kind of close to the ice edge. So one could argue maybe it advected, maybe it didn't advect in. It's hard to know, but it's certainly growing under the ice. And it's its high concentration is down to below 50 meters. So this is a robust bloom. And then in the Chukchi Sea in 2001, there was, this is in northern Chukchi Sea, there was some sampling done in conjunction with the crews. They weren't looking for phytoplankton, but what they did was they saw high chlorophyll concentrations. This is up to 5 micrograms per liter here, up to 15 at station 23, right there, under the ice. But what they attributed it to was ice algae falling off the ice into the water column, which is almost certainly not what it is, because there's way too much chlorophyll here to be, there's never anywhere close to this much chlorophyll in the ice, so that can't possibly be what it is. And so they probably saw an under ice phytoplankton bloom, but they didn't know they were seeing an under ice phytoplankton bloom, but I'm pretty sure that's what it is. In Resolute Passage, here there was it was basically an ice camp. So they do a lot of sea ice work in Resolute. And here they got pretty good measurements, because they didn't just see increased chlorophyll. They managed to measure lots of things in conjunction with it. So here they looked at, this is what the ice cover was like over between May and July. So the ice cover was about 1.8 meters, a little bit thinner near the end. And this is snow depth here. So you can see the snow is disappearing. Here's a rain event here. And then this is the PAR, which is photosynthetically active radiation, so visible light basically under the ice. And you can see after the rain period, which basically melted most of the snow, the transmission of light through the ice increased dramatically. And we got all this light under the ice. And associated with that increase in light, there was this big increase in chlorophyll concentration, all the way down to 90 meters. And so this was a pretty good documentation of an under ice phytoplankton bloom in Resolute, in the Canadian Arctic archipelago. So there's been hints, yes, all right. Occasionally they'll find some hints of an under ice bloom. Nobody really made much of a big deal about it. And if you go to Web of Science and you just say, let's search this term, under ice bloom or under ice phytoplankton, 5 to 20 times a year somebody mentions it. And then in 2012, suddenly the number of under ice bloom references has gone through the roof. And so it's become much more on people's radar screen now than it had been before. And I think the reason is because they're much more well documented now than they have ever been before. And so what I'm going to do is I'm going to present you 2 case studies showing an example of what these under ice phytoplankton blooms look like. One is a really nice temporal analysis that I was indirectly part of. And this is in the Arctic and the Resolute in the same place that I just talked about. But it's a different year. It's a different bloom. And then a detailed spatial analysis. And this was IceScape 2011, I was chief scientist on this particular cruise. And We could only sample the under ice bloom once, but we sampled the heck out of it the one time we did. So it's a really nice spatial analysis of the bloom. And we measured all kinds of properties. We got really lucky with that one. So this is where, right there, that's where Resolute is, and this is where the study site is. And so it's in between a bunch of islands under the ice. And so this was done in 2010. And ice thickness was about 1.25 to 1.45 meters. It didn't really vary very much. So there's a fair bit of ice. The air temperatures started out cool in May, and most of these plots I'm going to show are from May through June. And you'd see the air temperatures cool, but then eventually, of course, it gets above freezing. Eventually, here's this snow melt as the air gets above freezing, melts the snow, and then melt ponds eventually form. I'll show you some really nice pictures of melt ponds. Melt ponds is basically just collected fresh water that sits on top of the ice after the snow melts. Eventually, that fresh water will percolate down through the ice into the ocean, but for a while, it sits there in ponds. And those ponds tend to transmit lots of light. This is the albedo. So the albedo is basically the reflectivity of the ice. And ice is really reflective, right? You've all seen ice before. It's very white. So the albedo is really high. It's close to 1. So it's about 0.9, between 0.8 and 0.9 for most of the time. It's going down because it's starting to warm a little bit. And then when the snow melt begins, the albedo drops. And when those melt ponds form, the albedo drops a lot. So what this says now that it's reflecting about 30% of the light, which means it's transmitting about 70% of the light. So now suddenly lots of light is getting through to that under ice phytoplankton bloom. Well, we haven't talked about that yet. PAR, so this is just the underwater light at different light levels. Again, associated with that thinning sea ice cover, melting snow cover. As soon as the snow melts, it's actually starting to increase here pretty well, but then it ramps up really fast as the snow melts and as those melt ponds form. So in 100 microeinsteins, or micromole quantum per meter squared per second, if you're more familiar with that unit, is a lot of light under the ice. In fact, algae that live in the ice can grow on 2 or 3 microeinsteins. So there's a lot of light. There's plenty of light here for phytoplankton. This is at 2 meters, even down to 20 meters, it's greater than 10 microeinsteins by June. So there's quite a bit of light underneath the ice at this period. This is the salinity. So what we see is, remember it's still all ice covered, and we don't have much evidence of ice melt yet for most of the time series, but then at the end, we get a lot of ice melt. And what that ice melt has done is it's basically stratified the surface water. And so this is about a little over 30 meters thick, this low salinity meltwater layer. And that's sort of prime habitat for algae, right? Because when there is no stratification, even though there's light getting down to reasonable depths, there's still too much mixing. And the average light level within the water column is too low for anything to grow. You need a little bit of stratification under certain circumstances if you're going to have phytoplankton grow. And so it's starting to stratify at that point. And so that's where we see this is now chlorophyll concentration. So for most of the period, just very low chlorophyll concentrations, down a little bit above 0. And by the end, chlorophyll concentrations are up above 15 milligrams per meter cubed. And you guys probably have a better reference point for how high that is, because during upwelling season here, you can easily measure 15 microgram. And that actually would be a pretty high concentration off the coast here during upwelling. And so this is a healthy phytoplankton bloom. Again, it's down to over 5 micrograms per liter, down to around 50 meters. So this is a really healthy bloom that was documented during this. The total chlorophyll accumulation is about 508, which is really high. There was a paper published, I remember when I was a grad student, we talked about it a lot, that the theoretical maximum chlorophyll concentration you can support in the water column is about 300, right? Because above 300, there's not enough light to support any more biomass. Well, this is up above 500. Not quite clear how they can support that much, but it was. If we look at how it was impacting the nutrient concentrations, so this is nitrate plus nitrate there, this one is silicate, and this is phosphate. So not surprisingly, pre-bloom, concentrations in the Arctic are relatively high. And then when that phytoplankton bloom takes off, the nutrients get drawn to zero. Basically, the Arctic is a very nitrate-limited system, which you can tell from here because the nitrate goes to zero much quicker than the phosphate or the silicic acid does. If you look at this total amount of nitrogen drawdown, you can estimate new production about 18 grams of carbon per square meter. So this is a useful number to keep in your head. There's going to be a couple numbers that I'm going to ask you to keep in your head. 18 is one. We'll get to the other one in a little bit. So that was a really nice temporal study showing the development of an under ice bloom. And this is going to look at it from a totally different perspective. And so this is Ice Cape in 2011. This was a cruise I was on. It was actually funded by NASA. It was the first cruise that NASA has ever funded. Exports, the one they just did, was only the second cruise they ever funded. And so this was the first one, and we got really lucky. We weren't out there looking for under ice blooms. We fortunately blundered into one. And the reason we were there was a few reasons. We were interested in the biogeochemistry of the Arctic, but this was a NASA-funded cruise, and so much of what we were doing is try to improve the algorithms that allow us to remotely sense the Arctic, including remotely sensing the sea ice, remotely sensing the open water. Remote sensing of ocean color in the Arctic is a nightmare. I just had a student defend 2 days ago, her PhD, and that's what she was doing, trying to get improved algorithms for estimating chlorophyll in the Arctic, because it's hard. And so we were out there to make a bunch of optical measurements, make a bunch of hydrographic measurements, and we just happened to have the right people at the right place at the right time. So it was very lucky. So we sampled over 200 stations on this. I'm not going to show you all of them. I'm just going to show you a subset of stations right here, 46 to 71. So 46 is, so what this is actually a MODIS image, so it's a visible image. But it's nice because it happened to be a sunny day, so we got a nice image. You can see the ice in gray really well. You can see the open water really well in black. These lines are the previous ice edge, so this right there is the ice edge while we were there. But this is about July 8th-ish or so. This took a couple days to do, about July 8th. So July 1st, it was down here. June 17th, it was there. June 3rd. So the ice is retreating sort of in this direction, in the direction that toward the north, actually toward the northwest. But I'm going to focus on these stations alone. So what I'm going to show you now is an animation. So I wish I could take credit for having produced this, but I can't. So what you're going to see, well, actually, maybe it'll just start. Nope. It won't just start. Okay, I will start it. So what's going to do is you're going to zoom in. You're going to see a ship is going to appear. There we are. And it's basically going to show us going on that cruise track. And what it is going to show is what we measured along this cruise track. So what it's going to show, you're going to see these little balls. These little balls there are where we sampled the water. Eventually, colors will appear. Purple colors are really low chlorophyll. Red colors are high chlorophyll. So we're in open water. This white is the ice edge that we're heading into. So we're still sampling. Now the colors are appearing. And you can see in open water, it's almost all purple. There's very little chlorophyll in open water. As we get closer to the ice edge, now we're in the ice. Now all of a sudden, we see this. Boy, it's going really fast on this computer. It's supposed to be a fast computer. We see this big, this intense red color under ice. And I have to say, we measured this in our underway seawater system, and we were sure that our system was broken. That there was no way, because this is 100% ice cover, that there was, my experience has always been, you go from the open water into the ice, the chlorophyll concentrations just get really low. You never expect the chlorophyll concentrations to go through the roof. This is 30 micrograms per liter chlorophyll in a layer 30 meters thick. So what we did was we got very excited when we sampled that on the way in. And so we turned around and sampled it again at much higher spatial resolution coming out to see if we could actually map this bloom. So it's still under the ice here. We're coming out into open water. And you can see the bloom is descending a little bit as we go out, and then there's the end. But we can see there's the ice edge, and you can kind of see this big phytoplankton bloom under the ice. And so we just got really lucky that we were there to sample it, and we sampled all kinds of aspects of this particular bloom, much more than anybody had ever sampled before. And so this is basically the ingoing transect right here that you can see. And so what we can see is, so we're moving, so this is the first station, we're heading into the ice. This is ice concentration here. So this is open water, this is 100% ice cover. We're heading in, and you can see very little chlorophyll in open water. There is some deep chlorophyll here. And it's kind of important to note the way the ice is moving, right? The ice is moving in this direction. And what that means is a few days before we were there, this area was also totally covered in ice. And what looks like it happened was whatever phytoplankton were there consumed all the nutrients and then sunk to the bottom. And so this is an old under ice phytoplankton bloom on this side of the transect. And so it's old enough that, in fact, there's no evidence of any chlorophyll here at all. It's all sunk to the bottom. Here it's in the process of sinking down, but it hasn't sunk yet. This is a brand new, fresh, just starting out bloom. Physiologically very healthy. In fact, if you sample a phytoplankton cell here and you sample a phytoplankton cell down there, physiologically they're indistinguishable, right? Even though this is down at almost 100 meters, you can't tell the difference. And this is, here we've got down to almost 100 meters, and the chlorophyll concentrations are still between 5 and 10 micrograms per liter. And in this layer, they're around 30 micrograms per liter. So this is a really, really intense phytoplankton bloom. And this is actually what it looked like, if you actually visually. When we were there, the reason we went into the ice in the first place was to sample the sea ice. So we were drilling holes in the ice so we could put our optical instruments through the ice. And when you drilled a hole through the ice, the water, it was just pea soup green. You couldn't even see the bottom of the ice. It was so green. It looked just like this. I've seen lab cultures in my lab that look that green, but I've never seen ocean waters that look that green, unless it was some eutrophic, horrendous, coastal mess. But normally you don't expect to see this out in the middle of the Arctic Ocean under 1.5 meters of ice. You just don't expect to see it. It was dominated by diatoms, big, fat, happy diatoms. A few species, Odentella, Pseudonychia, Fragilariopsis, and so a few dinoflagellates. But mostly it was diatoms. To put the chlorophyll concentration in perspective, so I used to work at NASA, as you learned before I got there, and one thing I did when I got to NASA was we started a chlorophyll database. And so this is chlorophyll from all over the world, and all of NASA's database. And this is the relative frequency of different total water column chlorophyll concentrations in milligrams per square meter. So that means if you took all the chlorophyll from the surface all the way down to the bottom, added it all up, how much chlorophyll would that be? And on average for the globe, it's about 46. So it'd be about 46 milligrams per square meter. The average value in our bloom was 840. And the maximum value was 1,291. That is the highest chlorophyll concentration ever measured anywhere in the world. And it was in the Arctic under 2 meters of ice. So it was a big shock to us to see that. And so chlorophyll concentrations there are really high. And we didn't know they were there, and we don't know how distributed they are. So it's kind of a big deal. If you look at the growth rates, so these are the growth rates. So this is inside the bloom, and this is outside the bloom in open water. So outside the bloom, those phytoplankton were growing very slow. Inside the bloom, the growth rates were as high as 1.4 per day. So everybody familiar with Epley's famous paper where he talks about the relationship between phytoplankton growth rates and temperature? And what that paper says at about 0 degrees, the phytoplankton maximally should be able to grow at about 0.59 per day. This water was 2 degrees below that, so it was even colder. and yet they were growing at 1.4 per day. So they're growing much faster than anybody would ever expected. This is for the first transect. This is for that second transect coming back out. So phytoplankton are growing really fast. If we look at how productive they were, this is going to be the second number I'm going to ask you to put into your head. This is net community production, which is, you can think of it as just primary production. It's actually an underestimated primary production, but it's okay, because it's still a big number. The minimum was about 52 grams carbon per meter squared, the maximum 135, and the mean was about 80 grams carbon. That other bloom I talked about was about 18, the one in Resolute. So this is much, even though that was a pretty impressive bloom, this is much more productive than that, the Resolute Passage bloom was. So the question is, what's driving these blooms? How in the world can you end up with a phytoplankton bloom that intense under the ice? And what adaptations allow phytoplankton to bloom like that under the ice? Well, we know the Arctic ice is thinning, and that's going to be a piece of it. And if we look at, I just love this video. And so this basically shows sea ice age in the Arctic. And so these bright white are old. So this is 4+ years old. So it's ages, but you can sort of think as age is thickness. For every year, it adds almost another meter of ice. So ice that's over 4 years old is going to be about 4 meters thick, roughly. First year ice is going to be about 1 meter thick. And so you can almost think of it as ice thickness. And you can see, this is January 1984. The Arctic is just full of really old, thick ice, right? So what happens over time? So what you can see is all kinds of things going on. You can see ice being flushed out of the Arctic here through Fram Strait. You don't see a whole lot of evidence of so much melting yet. It's mostly going out this way. And the reason it did is because this is due to the Arctic Oscillation. So the Arctic Oscillation, the wind patterns were such that the winds were blowing a lot of ice out. But eventually, you will start to see these. So the gray is first-year ice. And what you'll see is eventually, in the summertime, we start taking big chunks out of the white, particularly on this there. We just lost a bunch of, so that's due to melting. Sorry, that's not due to advection, that's due to melting. And when we get to 2007 was the event that got me into Arctic research to begin with. And so we're losing more and more. You're seeing there's less and less white. 2006, this is the big one here. There. So there, 2007, we lost 23% of the summer ice was lost in 1 year. And now you can see there's just, it's into death throes, right? There's just hardly any thick ice in the Arctic left anymore. It's all, we're still getting a lot of first-year ice forming, right? So the gray is still extending pretty far, but there's very little of that thick ice anymore. So we're basically seeing a big expansion of thin first-year ice, which is really important. We're also seeing thinning snow cover. So this is from 1950 to about 2010. And you can see it's dropping at about 0.3 centimeters per year, the average snow thickness. So you got less snow, or you got less thick ice, you got thinner snow. And what that's going to do is it's going to transmit a lot more light. So this is basically a camera looking up. This is an area of thick snow. This is an area of thin snow. More light's going to be transmitted to the water column. So what's driving them? Well, in one respect, it's because this is what the Arctic used to look like. This is the old Arctic. And this is the old Arctic. That's what that ice pack looked like. This is the new Arctic, right? Much more thin ice and much less thick ice. And this is what it looks like now in the summer. You don't see those thick ridges anymore. You see melt ponds as far as the eye can see. And these melt ponds transmit a lot of light. If you look at where this is a melt pond, this is a snow-covered area. This isn't even snow-covered. This is just this bare white ice here, which is not snow. It transmits about 15% of the incoming light. Melt ponds transmit about 55%. So there's a lot more light getting through these melt ponds than previous. So that's a big piece of the puzzle of why these blooms are taking off. There's another really interesting thing about these, if you're a phytoplankton physiologist, as I am, is that these phytoplankton living there are primed to bloom. So this, strangely enough, so these are the relationship between their photosynthetic rate and how much light there is. And what you can see is that open water phytoplankton, even though they're living in open water where there should be lots of light, right? They do not have the capability to photosynthesize very rapidly. And so if you look, the maximum photosynthetic rate for these under ice phytoplankton is about over 2 times that in the open water. Not only that, the slope of this line is the photosynthetic efficiency. How efficient are they at using light? And they are twice as efficient under the ice as they are outside the ice. So as soon as they get a little bit of light, they just take off. And that's why those things bloom so fast. If you look at their actual quantum yield of photosynthesis, basically how much carbon do they fix per mole of photons that they absorb. The under ice phytoplankton are about 4 to 5 times more efficient at fixing carbon for a given amount of light than their open water counterparts are. So they do much better. Their maximum growth rates are higher by a factor of 5 potentially. And if you look at their photosynthetic pigments per chlorophyll, they're packed with pigments, so they can take advantage of what light they get. They're also, this is sampling date. This is pre-bloom and post-bloom. This is for another under ice bloom. And what they've also shown is that these are sunscreen pigments, these carotenoids and xanthophylls, so they're photoprotective. So they actually photoprotect themselves from too much light. So too much light is bad for phytoplankton too. So they're really physiologically primed to bloom in these particular areas. All right, so how do we detect these things? How do we find them? How do we know how widely distributed they are? It's really difficult. What we did, there's been cruises and field camps. Those are the 2 examples I've shown you, so you can do that. But there's no way you can sample the whole Arctic with cruises and field camps. You just can't do it. It's just too hard of a place to sample. It'd be great if we could do it with remote sensing. If somebody could develop a sensor that can see through that ice, I would be thrilled, but that's not going to happen. Gliders and AUVs are potentially useful. AUVs maybe more so. Gliders are bad in the Arctic because 60% of the Arctic is continental shelf and the waters are too shallow. They're just not good for gliders. Gliders need nice deep water. So that's probably not going to work. Some things that have been tried is BioArgo. And so this is some BioArgo float data. And this is Greenland right there. So it's basically off the east coast of Greenland. And this is sea ice concentration. Whether this is an under ice bloom, it kind of sort of is. It's not really 100% ice cover, which is normally what you'd see, so it's pretty broken up ice. But you can see this is chlorophyll concentration, well, from fluorescence, from the BioArgo float. And you can see that the bloom, there was a big bloom starting when there was still lots of sea ice around. And this is 2012 and 14. So BioArgo is a potential tool we can maybe use to monitor them. BioArgos don't deal well with ice. They're getting better. They can detect the ice and move away when they have to. But you don't find many BioArgo floats deployed under the ice. Ice-tethered buoys are a possibility. So this is a study that was done in the Chukchi Sea where a buoy was put on the ice and the ice was allowed to drift around. And there was a camera on it looking up. Very simple technology. And you could see over time, this is March 9th to September 1st, where there was this big under ice phytoplankton bloom. In fact, this was the exact same place where we observed ours the year before. And so that was actually 2 years before. So this is a possible technology. This is one we worked on. It's like, all right, we can't directly remotely sense them, but is there a way we can maybe indirectly remotely sense them? And the idea behind this is that phytoplankton bloom, if there's nutrients in the water and the lights come on, phytoplankton will grow, and they will consume those nutrients. That's their assumption. So what that means is if you've got ice and that ice disappears, right, what you'd expect is the phytoplankton should take off, right? If the phytoplankton don't take off, what that suggests is that the phytoplankton probably grew while the ice was there, and there's no nutrients left, so they can't take off. And so we use the relationship between the timing of ice retreat and how that phytoplankton bloom. So in the marginal ice zone, what you expect, the ice retreats and then the phytoplankton start to grow. So we looked for this kind of a signal. If it was an under ice bloom, as soon as that ice retreats, you see high concentrations of chlorophyll in that water, which meant obviously there was a bloom there, and those chlorophyll concentrations should be increasing. If it doesn't do anything, that means there was probably an under ice bloom there. So we're trying this in other areas. We know it works here in the Chukchi Sea because we measured it in the Chukchi Sea, and we're trying it in other places to see if this particular technology works. So how widespread might they be? Well, this is a sort of a back-of-the-envelope calculation. And if you just look at the Arctic, 55% of the Arctic is continental shelf. If you look at where you've got high enough nutrient concentrations on the continental shelf under the sea ice, what you end up with is about 25% of the Arctic has the conditions that would support under ice phytoplankton blooms. So this is really just a quick and dirty way of doing it. Somebody did it more rigorously, Horvat, in 2017. And he basically did an optical model and said, what fraction of the Arctic Ocean has enough light for an under ice bloom, regardless of nutrients? And this is done over time. So early on, this is May, June, July. May, there's just not enough light anywhere for any under ice phytoplankton to grow. By June, early on in the time series, there wasn't enough, but now there is enough for about 15%. And in July, about 25%, which is amazingly close to the 25% we calculate from our back of the envelope calculation. So maybe 25% is not a bad number. So a question we have, and a question people always ask is, are these new or have they always been around and we just didn't see them, right? Unless you go into the ice to sample them, you'll never know they're there. And even people on icebreakers typically don't bother to go into the ice. You're on an icebreaker in case you run into ice, but most people aren't actively sampling into the ice. So are they new or are they just newly recognized? So if we look at all the places where under ice phytoplankton blooms have been observed, this is all of them that I could find. And this is May 2016. And you'll notice all of them, this is that same map that I showed you, where this light gray is first year ice, so it's young ice. They're all in first year ice now. But what did those look like in 1984? In 1984, almost all of them, there's no way an under ice bloom formed here, or here, or here, or here, or there, or there. Maybe there, not there, probably there, and we don't know there because we don't have any numbers there. But many of these places, there's no way there was an under ice bloom because there was too much thick ice around. So in that sense, I would argue that they're a new phenomenon, at least for most of the Arctic. For parts of the Arctic, southern Chukchi Sea, maybe not. But for everything else, yes. So I think what we need to do is revise our phytoplankton phenology now. It's not as simple as just saying, when the light turns on and the ice retreats, the phytoplankton will grow. Because now what we're seeing is the phytoplankton are growing much sooner, much earlier in the season than they ever were before. And this is where the phenology becomes important. And we'll talk about the consequences of that in just a second. And so it's not as simple as this. And we've got under ice blooms, not everywhere, but often. And they've got to be considered. So why do they matter? Why do we care about under ice blooms, right? It's just, I mean, who cares if it's an open water phytoplankton bloom or it's an under ice phytoplankton bloom? It's still a phytoplankton bloom, right? It still provides food for the ecosystem. Well, I would argue it does make a difference. So the one thing we know is productivity in Arctic is increasing. I haven't presented you any of this data, although I could have. And so this is basically, since between 1998 and 2012, productivity in Arctic Ocean increased 30%, which is huge. We just redid this study. That was my student's defense. All the way up to 2018, productivity in Arctic has now increased 57%. 57% in 20 years. Imagine an entire Arctic basin, productivity increasing 57% in 20 years. That's huge. So productivity is increasing, but this is just the open water component of the production. Now we've got productivity going on in the ice-covered parts as well that is virtually unquantified. This is unaccounted for. Now, remember I told you to remember that other number? So this is, I've published this. This is from my paper, 2015. This is a map of productivity of the Chukchi Sea. This is where that under ice phytoplankton bloom was. And if you look at what productivity we estimated for that region, annual, it's about 5. So satellites say there's 5 grams of carbon per meter squared per year of production here. What was the number we measured in IceCape? 80. It was 80. So we're like more than 10-fold low. So what this means is 90% of the production in the Chukchi Sea, has always been recognized as one of the most productive seas in the Arctic, based on open water productivity numbers. 90% of it is going on under the ice that we've never been able to account for before. So our estimates of open water production are fine, but estimates that does not reflect total production, which we need to account for. Particularly on places on the continental shelf, under ice phytoplankton blooms are likely to lead to more carbon reaching the seafloor. The reason that is because those blooms happen very early in the season, before zooplankton have had a chance to catch up to them, and they're happening in waters under the ice that's 2 degrees below zero, where metabolic rates are very low, and things just can't feed enough. And so most of that stuff is going to be feeding benthic environments. And so we're likely to potentially see a shift from a benthic-dominated community to pelagic-dominated community to a benthic-dominated community. And the last thing is, coming back to the title of the talk, it's changing the timing of productivity. And there are so many animals that either migrate or live in the Arctic Ocean that rely on being there when that productivity is at its peak. And the productivity is now as much as a month earlier in some places than it used to be. If you're a gray whale, you really don't have the option of getting up to the Chukchi Sea a month earlier than you have historically. If you're an Arctic tern, coming all the way from the southern hemisphere, you can't get to the Arctic fast enough. And so to me, this is the scariest part of this whole changing Arctic Ocean is the timing. Is because, yeah, there's more production, but can the ecosystem adapt to that changing timing of that more production? So with that, I will take any questions. Yes. I didn't even know that was a microphone.
Okay. Has anybody done any population genetic studies on these phytoplankton blooms to see, where they might be coming from and map that out?
You mean, no. The short answer is no. I will say that there was genetic data collected during, even as far back as 2011 when we did our cruise. And we were collaborating with the Canadians. So they've got all those data, but I don't know if they've done anything with those data. So it would be really nice if somebody would do that, but they haven't been done yet. Yeah.
Just lean over a little. Some of the diatoms that you showed, the diatoms that you showed are ones that are found elsewhere as well. Are these, you also talked about how they were more adapted in the under ice blooms to be faster growing, more productive.
Right.
So are these different species, or are they different clades within those groups?
No, so it's not even different species, probably different groups. In the open water, well, it depends on when you mean in the open water. So what happens in the Arctic, there's a very quick succession. So you got the big diatoms start to bloom. When the nutrients get depleted in open water, it switches to picoplankton. So it's all pico-eukaryotic mostly. There's very little cyanos in the Arctic. But the reason we were interested in the species composition there was because we wanted to make sure that those diatom species were not sea ice diatom species, and they aren't. But those things will still bloom in open water for a little while. One of the reasons why the physiological responses of the algae in open water are so bad is because they've run out of most of their nutrients, right? And so you just can't maintain high photosynthetic rates if there's no nitrate around, if there's not much nitrate around. So it's probably the same group for a little while, but very quickly those things get outcompeted by the smaller guys that can better compete for the low nutrient concentrations. Yeah.
When you're comparing chlorophyll values between the under ice blooms and the open water blooms, do those big differences necessarily reflect the biomass in terms of carbon, or could these blooms just be
Making more chlorophyll? It's a little of both, but it's the pattern in carbon is exactly the same. So there's higher chlorophyll to carbon ratios under the ice than there is in open water, as you would expect. And so, but it's not that big of a difference. You know, when you look at the magnitude of biomass in terms of chlorophyll, you know, it's probably, I don't even know, it's 3-4 times, well, even more than that, under the ice at its peak, right? And the changes in carbon and chlorophyll are maybe 50%. So it can explain a little bit of the difference in chlorophyll is always a dangerous metric to use for phytoplankton biomass. Carbon is always better. The problem with the carbon is there's a lot of other microbial carbon in there too that we don't want to, at least chlorophyll is specific to phytoplankton, whereas, you know, as we measure just particular organic carbon, it's not.
Has anyone looked at this in the Antarctic as well?
That's where I got my start, was the Antarctic. So no one's looking for these in the Antarctic yet. Not that they shouldn't, because when we saw it, I would have said we shouldn't be looking for these in the Arctic either. I was on a cruise, this is a long time ago, in the late 90s, and we saw it plain as day. Whenever we went into the ice, the chlorophyll concentrations in the water column just dropped like a rock. You know, in the open water, they were high. Under the ice, they were really low. And this was even when there was just like thin tongues of ice. They would be really low. And that's sort of where I got my mindset. And that's what I expected to see when I got to the Arctic. That's why we were so surprised when we went into the ice and the chlorophyll concentrations kept going up and up and up and up. So the reason it's different in the Antarctic is the snow thickness is a lot higher in the Antarctic. I don't know that I've ever seen a melt pond in the Antarctic before, because it's a lot colder. I mean, eventually it melts. And it's still a lot of first-year ice, so you'd think you could form melt ponds, but they just don't really ever form, so that water never accumulates in the surface, so it never transmits enough light before the ice just melts.
Well, thank you again, Kevin.
Sure, thank
and
you.
I hope you can all stick around. We've got beer over here from the Brew Club, so please join us for that.
Thanks a lot.